Dr. Bonato is the director of the Motion Analysis Laboratory at Spaulding Rehabilitation Hospital, located in Charlestown, Massachusetts. He's an assistant professor in the Department of Physical Medicine and Rehabilitation at Harvard Medical School. He's also a member of the affiliated faculty of the Harvard-MIT Division of Health Sciences and Technology and an adjunct professor of biomedical engineering at the MGH Institute of Health Professions. He's an international expert in rehabilitation technology with special emphasis on wearable technology and robotics, and he is our colleague in our Boston Rock. He is the director of the Instrumented Outcome Measures Core. So welcome, Dr. Bonato, and we're so happy to have you share your expertise with us today.
Well, thank you very much for the kind introduction and the invitation. I'm going to use the next 27 minutes, because we use already 3 for the introduction, for the talk. And I'm going to talk to you a bit about the use of technology to derive outcome measure. I wasn't sure whether or not this was going to provide CME credits, but I'm used to do these things. So unfortunately, I have no conflicts of interest with all the companies, fantastic companies that manufacture some of the technologies that I'm going to describe. We're going to have a focus on human motion. It's not a new thing, and some of you might have recognized Muybridge's work here. So obviously, we have been looking into characterizing functional limitations in individuals by looking at the movement characteristics that are associated with the study of such movements. And there is quite a lot of interest for the use of sensing technology that will allow us to do that outside of the laboratory. I just picked 3 papers. These are RI as opposed to OA, but there are plenty of papers actually that show a significant interest for measuring activity level in the field. And so in this case, you would utilize systems like the sensor-aware system that you see here by Body Media, a system that has been around for quite a little while now. It has been characterized for the purpose of assessing activity levels by utilizing both the use of accelerometers that are actually embedded in the unit that is strapped to the upper arm, as well as other additional sensors such as temperature gradient sensors that's actually embedded in the system that allows you to refine your analysis that are actually performed on the basis of the accelerometer data. There is interest for monitoring as well, facilitating exercise. There are all sorts of systems that have been utilized both for the purpose of assessing exercise compliance as well as the purpose of encouraging individuals to be active as part of an exercise-based intervention. This is a paper that actually uses the stopwatch, but there are all sorts of studies that are ongoing utilizing systems that are consumer products, like the Fitbit, for instance, that I trust many of you at least have seen, because the system has received so much visibility out there. And I assume that, like our group, many of you might actually be using such technology to provide feedback to patients when you actually set up an exercise-based intervention, and you're not extremely concerned about the accuracy of the system, but you're more concerned about the capability of the system to provide feedback to the individual so that you can keep them active. And there are also a number of papers out there that focus on the assessment of activities as they relate to functional limitations. This is one of such papers, where there is a stronger interest for understanding what the first speaker earlier mentioned, some of the biomechanics of movements. In fact, for instance, in knee osteoarthritis, at least for those cases that do involve the medial compartment as opposed to the lateral one, right? You would have very well-established measures that you would gather in a laboratory setting. For instance, you would look into peak torques, adduction torques at the knee, and look at the abnormality of it, so the increased peak abduction torque that you would have at the knee as a measure, essentially, of the severity of the condition that affects that individual. So in the laboratory setting, we do, in fact, gather these more accurate measures, typically by utilizing a stereophotogrammetry system. So a system that it's based on video cameras, the use of reflective markers, anatomical or biomechanical models that are associated with the study or they're being developed in the past to study joint motion. And the output typically would look like this clip. This is obviously not neither RA nor OA. This is a stroke individual pre and post intervention. You can see the typical pattern of hip circumduction in these individuals, so different from the population that we're focusing on. But you see the type of gross biomechanical observations that you would gather, and you overlay this type of data with mechanical models that allow you actually to look at both the characteristics, the kinematic characteristics of ambulation, so knee flexion extension, hip flexion extension, and joint angles in different planes, as well as the kinetics, so the amount of forces generated by muscles that control different joints, and the torques and powers produced at different joints. So, but unfortunately, these systems have limitations. Traditional stereophotogrammetric systems are certainly limited to the use in the laboratory setting, which is what the papers that I mentioned earlier obviously want to overcome. You will require an obstructive view of the subject because obviously the cameras cannot be viewed, cannot be blocked so that the model can actually be applied properly, and they're certainly not suitable for long-term interventions. So even in the clinic, when you want to perform a study, for instance, that will characterize the intervention that happens in the inpatient-outpatient setting, it's actually quite complex and cumbersome to utilize this type of tools that are biomechanical in nature. So one first attempt to overcome these limitations was by many the one of utilizing or developing first and utilizing next systems that we define as markerless. So they actually provide the capability of tracking the biomechanics of motion, but they actually do not require that you position reflective markers or use spatial cameras, if you will. And this, to some extent, is actually the generation of the Kinect and Wii type of systems that are relatively sophisticated, actually, from an engineering point of view, and they usually utilize a number of hybrid sensing technology in order to be able to gather the information without utilizing, in fact, traditional reflective markers. There are now a number of systems that our group and others have been trying to play with, such as the lip motion that you see on the bottom right of this slide, that essentially captures the movements of the hand without actually having to position anything in particular on the hand itself. It's unfortunately only suitable for to be utilized in a small volume, and it doesn't necessarily adjust to abnormalities in postures of the hand. So it essentially assumes, the software that actually runs it assumes that the monitoring is of a person that's capable of extending and flexing the fingers in a sort of normative way. There are also experimental, not off-the-shelf system. The lip motion is actually a system that you can purchase for a relatively small price. I think it's about $40 to $50, but it's designed actually to work with Apple computers. But there are now, on the research side of things, there are now systems that are actually portable, like the Microsoft Digit system that you see on the upper right of this slide. And these actually allow us to collect data in a markerless way. They're purely biomechanical. However, these systems, they're not ready as yet to actually get full biomechanics of motion in the field. And so we have been utilizing a variety of different technologies than the one that I just showed you a minute ago to implement the vision that you see summarized in this slide. And so this is the objective. This addresses the objective of monitor individuals in the home and community settings by positioning wireless sensors to monitor different body segments or gather physiological data, or embedding sensing technology into clothing items through e-textile solutions, and relay the information through a variety of communication capabilities to the end user, whether it's for a personal emergency response system or for feedback that has to be provided to a family or caregiver or the clinical team, or back to the subject as is actually done in some of the commercially available systems like the Fitbit that I mentioned earlier. This is, again, not a new idea. In fact, this idea has been around for now about 70 years. In fact, the first person that thought of it is the person depicted in the slide here, Norman Holter, who at the end of the 1940s, early 1950s, started appreciating that there was quite a lot of potential in gathering data to study the cardiovascular system outside of the clinic. And clearly the technology that was available to him 60, 70 years ago was very cumbersome. Just to collect data from a short period of time, he had actually to use that humongous backpack that had to be carried by the individual during the cardiovascular monitoring. Now that type of capability is actually provided by systems like the one that you see on the bottom right. That's a standard EKG system, a standard EKG lead system that's about the size of a pager that allows you to collect data for about 2 to 3 days. But there are also remapping of non-conventional EKG recordings that you can now achieve with watches. And so although the first watches actually came up with essentially the capability solely of monitoring heart rate, more recently a number of groups have actually looked into remapping data that you would collect with non-conventional leads into traditional leads so that they can be interpreted clinically more easily. There are two types of technologies that people have utilized in these contexts: e-textile and wireless solutions. In this slide, I show the screenshot of two companies that I'm not even sure they're in business any longer, but I often use this slide to acknowledge the contribution of two major groups. One, Georgia Tech, led by Yaya Raman, Sandaraz and Yaya Raman, who actually developed this smart shirt by embedding fiber optics into the fabric of an undershirt that actually allow them to plug virtually any type of sensing technology into the shirt, into the fabric, as if that happened to be a computer bus. And then on the bottom right, work done by Harry Azada at MIT, who developed the first photoplethysmographic sensor that actually allow individuals to gather heart rate and oxygen saturation data in a rather unobtrusive way. You can see all the electronics is actually mounted on a ring. That's the reason why they call it the ring sensor. And that included both the photoplethysmographic sensing technology as well as the wireless technology that they eventually licensed to the company Millennial Net that you see there. There are now many more technologies. The two that I just referred to are technologies that were developed about 15 years ago. There are now all sorts of commercially available systems that allow you both to collect really easily movement data, such as you would do with an extension, essentially, of a pedometer or an activity monitor, as well as physiological data that you might have an interest in. So there are some of these platforms that are actually purely for researchers who have an interest in plugging into the platform, modifying it, such as the LilyPad or the Shimmer platform on the bottom right, as well as the MetaWatch that you see in the center of the slides on the bottom, which is essentially a gateway or a data login type of system that Texas developed about 3 years ago now. There are then easier to use off-the-shelf systems like the systems commercialized by APDM, as well as systems that are really designed for the purpose of delivering this type of technology to the public at large, so as consumer products such as the Fitbit or the Fuel Band that have, though, interesting characteristics even for clinical studies. So imagine, for instance, if you happen to be interested in monitoring the activity of stroke survivors, the activity of the affected side, the stroke survivors, and providing it's very easy visual feedback to these individuals concerning the use of their affecticide. You could simply utilize the LED system that's embedded in the fuel band and set targets that would match essentially the activity of the contralateral side. So these are all systems that are not necessarily designed for clinical applications, but they do actually provide capabilities that might be of interest in some of the clinical applications. Less easy to use and less readily available are systems that actually embed this sensing technology into the fabric of undergarments. These are some of the examples of the technologies that are available out there. There are still technologies that are essentially utilized primarily in the research field that they don't provide easy data logging capability and is of access to the data that you are collecting. Everything typically goes through a gateway, which is a cell phone. This is a slide that I borrowed from Julien Penders. He was one of the leading individuals in this field. He runs the Human++ program at IMEC in the Netherlands. IMEC has, I know we have a Dutch person, so IMEC actually has the headquarters in Belgium, but their wearable technology program is run by a group in Eindhoven. And they're doing really fantastic job delivering all sorts of systems for research purposes, not for consumers or clinical products, but for research purposes, they're delivering fantastic systems to the community. So what do you do with this technology? You do essentially three things. You first monitor activities, and so your first task will be identify motor activities performed by individuals that are part of your clinical studies. An example is a study that we ran in the past with Marilyn Moy in patients with chronic obstructive pulmonary disease to assess the capability of combining, or the possibility of combining motor activities and associated systemic responses to predict exacerbation episodes in this population. So in this case, you basically focus on extending what typically a pedometer would do or traditional activity monitors would do by utilizing technology that you deliver by using one of the platforms that I mentioned earlier, that I showed earlier in the slides. The second objective of this technology is to assess quality of movement. And so in this case, you utilize systems that have different characteristics. The ability to access raw data becomes essential as opposed to have significant data reduction on the sensors. So there is nothing that it's actually making your data set compact on the sensors as it would typically happen in pedometers. You would want to have the all output of the accelerometers, and you would use it. For instance, this is another project that we have run in the recent past. You would use it to assess functional limitations or severity of impairments in the populations that you monitor. In this case, we monitor stroke survivors during the motor recovery process, and we match essentially utilizing accelerometers, the functional ability scale score, the Fugger-Meyer score, and things that would require an actual examination of the patient in the inpatient and outpatient settings, which unfortunately clinically, those scales are seldom utilized because therapists have to trade off between time devoted to the therapy and time devoted to the assessments. And so we're trying to provide these tools as a way to collect data during an intervention and then infer what clinical scores would be if the therapist actually at the time to perform those evaluations. And finally, this is a bit outside of the area of interest of this group, but this technology has been utilized quite extensively to enhance the functioning or how the control of mobility devices. And this is because of the explosion of systems in rehabilitation that leverage robotics to augment function. And so these technologies often utilized to gather contextual data to provide information to the controller so that the system can be controlled in the best way possible. And you see here a picture of a project that we ran a few years ago with Joel Stein and Dr. Mavroidis and Arthritis University, where we play with robotically actuated knee braces in this regard. So, but back to the monitoring goals, and perhaps with a bit more focus on something that seems to be this center of the attention of this group, let me show you a couple of examples. So the first one that I want to comment upon is it's an instrumented knee sleeve that we developed over the past year, where you can see that we essentially leverage the fact that some of these patients were wearing already a sleeve and monitor consequently the movement of the knee and activity in the context of different activities that are performed by the individual. So what we have is an e-textile sensor that's actually embedded or integrated into the knee sleeve. That's a simple piece of fabric that changes its resistance as you stretch it. And through a conductive yarn, we actually can tell essentially if the sleeve is stretched or not, and therefore whether or not the subject is actually wearing the sleeve. We have a platform, which is an off-the-shelf platform. It's called Shimmer, that we embedded in that enclosure that you see in the goniometric system that's attached laterally to the sleeve through magnetic buttons that provide both mechanical stability as well as electrical contacts, as well as we have a simple potentiometer that's actually embedded in the system that you see depicted in this picture. So what we do with that is that we use the accelerometers to identify the activities that individuals are engaged in. We use the goniometer to study the knee flexion extension pattern in the context of the different activities that the subject is engaged in. And we use the e-textile sensor to provide feedback to the subject during the day in case the subject is actually not wearing the sleeve. So the system talks to a cell phone, the cell phone that the subject is supposed to carry. We hope at least that the subject is going to be compliant with carrying the phone. Although we have other embedded solutions that we could implement. But the non-invasive ones are based on cell phones. Assuming that the subject carries the phone, then periodically we essentially do what's called a ping, right, of the phone from the instrumented sleeve. And if we see that that e-textile sensor is not stretched, it means the subject is not wearing it. And so we actually send a reminder to the subject that he or she has to wear the sleeve. We have utilized the sensing technology also to assess compliance with exercise interventions, but also to assess proficiency. And so the best slide that I have is actually a study that we're running with Peter Wayne at Brigham Women's Hospital. Is very interested into alternative medicine type of interventions and exercises that are actually based on Tai Chi, which in numerous populations that we see in a rehab environment is an intervention that's widely utilized. But one of the issues that we have is whether or not subjects are actually compliant with their classes, which I guess you could assess by just taking signatures as you do in class when you go to college, right? But the other thing that we don't know is whether or not they're actually performing the exercises properly. And so one thing that we wanted to do is to see if there was an association between the proficiency of individuals in the classes that Peter is offering as part of a number of interventions that he is running at the Osher Center, which is the center that's focused on alternative medicine intervention at Harvard, and the outcomes. And so what we're doing is that we're studying how biomechanically people are performing these tasks, but also we are setting up, we actually set up a platform that allows us actually to derive essentially a matrix that's very similar to the matrix that you would derive from the stick diagram that I showed you earlier, so the biomechanical evaluations, but we do it purely on the basis of sensing technology. And one thing that we're doing at the moment is to do what we call sensor reduction, is to figure out how few sensors we really have to put on the person in order to be able to assess proficiency. So I don't have an answer around that as yet. Then the barrier that we have to break in order to be able to process these data and then provide feedback to individuals is to make sure that the data becomes available to the clinical team in a timely manner. And so what we do to achieve that goal is to relay the data through either an access point or a cell phone technology to a remote site. And it's often the case that we want to have the ability to actually interact with the subject. And so this is a screenshot from an application that we have developed a little while ago that we have revisited recently, and whereas the original platform was implemented in a traditional server-based modality, the more recent version of the system that we have developed, it's cloud-based, which allows scalability and ease of access. And this is a version of the system that we actually have developed as part of the center grant, the R24, that Alan is running at Boston University jointly with an R24 center grant that was received by IRC. And that's a platform that during the summer we're actually going to make available to the scientific community. So if you have an interest for this sort of tools, just let us know, because soon this platform will be released. So I want to conclude with a few considerations of where this technology is going, so that in case you have an interest for deploying this technology in your studies, you have an idea of in which direction the research is moving. There are 5 challenges that we envision will be addressed over the next few years. And the challenges are related to the ease of, or how easy it is to wear the sensing technology that we want to utilize. So we've seen a lot of work over the last year or so toward developing systems with a form factor that allows subjects to wear these systems, and even brag about it as you do with the Nike Fuel. We have seen a lot of development in the area of minimizing power requirements, which is still quite an issue for some of the off-the-shelf systems that people utilize in research, where such systems have to be recharged periodically every few days in order to actually gather data. We have seen significant challenges as well as significant work in the area of analyzing these large data sets in ways they are creative and not traditional to address challenges that are associated with deriving clinically meaningful information from these large data sets. We have seen significant challenges and work over the past few years in the area of plugging directly the results of the analysis of these data sets into electronic health records. And lastly, we are witnessing quite a revolution in terms of embedding sensing technology in items that individuals would wear for other reasons, such as the Google Glass platform, which we have been using extensively over the past year. Our long-term vision is to monitor individuals in the field. This is a picture taken by one of my postdoctoral students, which nicely characterizes what we want to do. Obviously, the fake sensors and data were not there. So we overlay that with the picture. That was taken where I grew up in Italy, and so obviously the place where all of us want to retire, I assume so. But the place where we want to be continuously monitored in order to be sure that we live a healthy life characterized by high mobility and activities. So I want to acknowledge our sponsors, our funding agencies, personnel in my laboratory, and collaborators that have contributed to the work that I quickly summarized today. This is a relatively recent picture from my team. I don't think that there will be time for questions because I took a tiny bit more time than I should. But my contact information is down there. You're welcome to drop me an email message, and I'll send you additional information as you request. Thank